Hi everyone, happy Friday. Thanks for coming. Happy to introduce Tracy Chin from the University of Washington. So Tracy is a fifth-year graduate student working under the supervision of Cynthia Vincent. She expects to graduate next year, and her primary research interest is combinatorics, real algebraic geometry, tropical geometry, and the intersections of these. Please take it away.
Yeah, thank you very much. Thanks so much for inviting me. So today I'm going to be talking about some joint work I did with Nathan Chung, Gaku Liu, and Cynthia Vincent, all of whom are also at the University of Washington with me. And so we have this preprint. If you're in, oh, what did I do? Oh, that's what I did. So yeah, we have this preprint out. If you're interested, this is a QR code to the preprint. And so it's on valuated delta matroids and principal minors. So basically the game plan is I'm going to talk about all possible combinations of these modifiers on matroids. So we'll start with just matroids, and then valuated matroids, and then delta matroids, and then finally we'll get to valuated delta matroids. So matroids, hopefully we've all at least sort of seen them. If you ask 5 different combinatorialists, you'll get 6 different definitions of matroids, but today we're gonna stick with this basis exchange version. So we have some set of bases, and it has this property that whenever we have something that's in one basis but not another, there's something else we can swap out with it to get to a new basis. Equivalently, these also have the strong exchange property, which basically says like whatever we're swapping in S, we do like the opposite swap in T, and both of them become bases. I'd say it's not obvious that these are equivalent, but they turn out to be. And another thing that one of your 5 combinatorialists might have told you about matroids is that you can also like classify them by polytopes. So we're gonna take our collection of bases, we're gonna plot their indicator vectors, and then we want that all of the edges in this polytope we end up with are in directions EI minus EJ. So for example, in this thing, this edge on the bottom here is E3 minus E4. And I think it's worth taking a moment to like think about why this comes from the basis exchange axiom. So if, for example, we have 1, 3, and 2, 4, why can't this be an edge of our polytope? We know that it won't be because this is a matroid, and so we don't get any edges in whatever direction that is. But like, why does that happen? And the answer is like, because of basis exchange, right? If we have 1, 3, and 2, 4, then we have to have something that we can exchange to get 2 new bases, and so those will also be vertices. And so in particular, like, we can't have this blue edge because it would intersect with this red edge. So once we have the blue segment and the red segment, because of how polytopes work, we have to have this whole square, and in particular, neither of these can be an edge. Okay, so one of the people's favorite ways to come up, here's something that is not a matroid. And the way we can see this is, so for basis exchange, if we take 1, 2, and 3, 4, there's nothing that we can swap out to get to 2 new bases. And in this polytope, because of that, like we get this edge between 1, 2, and 3, 4. So one of people's favorite constructions of matroids comes from linear subspaces, the Grassmannian. And so if you take your favorite rank D matrix, and you look at which submatrices have non-vanishing determinant, these will give you the bases of a matroid. So here, I cooked up this matrix so that it's the same matroid we've seen on the last couple slides. Okay. So crash course on matroids over. Now let's talk about valuated matroids. So because we have this strong exchange property, it's pretty easy to just like put some values on it and get some sort of valuated strong exchange property. So this should look a lot like the strong basis exchange axiom. Now we want that whenever we have 2 bases, S and T, there's some things that we can swap out so that our sum is now less than or equal to our original sum. And we call this space the dressing. So one thing to note is that if we look at all of the things that aren't infinity, that has to give us a matroid. Because if PS and PT are both not infinity, we have to have not infinity on this side. So there has to be some sort of basis exchange we can do. Turns out that these also we can talk about with polytopes. So if we consider this function p as some sort of height function, we're going to take our basis polytope and like lift it into one dimension higher. And then we're going to take that new polytope, hold it over our heads, and look at what faces we can see. So in this case, those red numbers are my height function, and I see this orange triangle and the blue triangle. If you want to do like actual math instead of pretending that you can hold a polytope over your head in arbitrary dimension, it's just the faces that have positive last coordinate of their inner normal. And so this will give us some sort of subdivision. No matter what the height function is, this gives us a subdivision. And evaluated matroids are exactly those height functions where we get a subdivision into matroid polytopes. So here, this is sort of maybe a dumb height function, but I'm going to take everything at height 0 except for this one thing at height 1. So in particular, if I take any like opposite pair of vertices, I can always do some basis exchange to get to another height 0 diagonal. So if I start at these two, I can exchange to like these two. But importantly, if I start at these two that already attain the minimum, there has to be something else that also attains the minimum. And because like this entire square is at height 0, like we can't break it up when we do our subdivision, and so we get this subdivision into two pyramids. So again, like the fact that the minimum ends up being attained twice because of this basis exchange, like valuated basis exchange, means that we have to get like some sort of square. And because we have a square, like any bad edge is going to go through the center of the octahedron. And since we have a square that occupies the center of the octahedron, we can't have any of these bad edges. Here's a non-example. It's sort of secretly the same non-example that we saw before. So here we're going to have 1s at these two vertices and 0s everywhere else. And then in particular, we get like this blue polytope in our subdivision. And that is not a matroid polytope because it has this bad edge going through the middle. And if we wanted to like see the exchange property, if we take these two corners that have 0s on them, all of the other diagonals have a 0 and a 1. So they'll be strictly greater. It turns out that like these octahedron examples, I mean, partly I was drawing the octahedron because it's like the only non-trivial thing in 3D and I can only draw in 3D, but also it turns out that sort of this is the only thing that can go wrong. It turns out that as long as all of your octahedrons have this minimum attained twice, so we get this orange square, then like we're good everywhere. We don't have to check things further apart than that on the basis exchange. Now, some of you may be looking at this condition. If you are appropriately Grassmannian pilled, you might say, wow, that sure does look like the Plücker relations. And it turns out that those of you who are Grassmannian pilled are correct. This is like the tropical version of the three-term Plücker relations. Okay. So to get into like why this makes sense, we need to do like a quick crash course on valuations. So we have a field K. We have a map from K to the reals union infinity, where our valuation is infinity if and only if we're 0. And then on the units of K, it should be a group homomorphism. And then it also has this non-Archimedean condition that says when we take a sum, that valuation has to be at least the minimum of the valuations we started with. So, some examples. If you enjoy tropical geometry, this is probably your favorite example. So these are like formal power series with rational exponents. And our valuation is just the smallest exponent that appears with non-zero coefficient. So you can think of this as like, what is the behavior of this power series as t goes to 0? Like, does it go to infinity? If so, how fast does it go to 0? If so, how fast, or is it a constant? If you want to impress your friends who do number theory, you can use the rationals with the p-adic valuation. So this is like how many powers of some prime p divide a rational number. Or if you are like me and enjoy edge cases, you can make any field into a valued field where you just send 0, the valuation of 0 is infinity, and the valuation of everything else is 0. This will, satisfy all of these conditions. So if we let valued fields into our lives, now we're going to take, again, a D by N matrix, this time over a valued field, and then we're going to define our function to be the valuations of these determinants. So in particular, because the valuation is infinity if and only if the thing you put in is 0, like the support of this thing will be the normal Matroid version that we started with. And it turns out that if you use non-trivial valuations, this gives you valuated Matroids. And we're going to call these representable. So for example, this is basically the same example I showed you before. So this is basically the same matrix I showed you before, except now we put this 1 minus t instead of 1. You can either check or trust me that these are the determinants we get. And in particular, all of them have valuation 0, except for 3, 4. The determinant is minus t, so t to the first is the smallest power of t we see, and so that has valuation 1. And we get the same subdivision we saw earlier. Any questions on valuated matroids before we move on to our next combination of modifiers? Okay. So delta matroids. My motto for delta matroids is they are what you get if you lock a combinatorialist in a room and you say you can't come out until you come up with the definition of matroids where the bases don't have to be the same size. So before we had like I and S minus T and J and T minus S. This time we're just going to say I is in the symmetric difference, J is in the symmetric difference, and then we're just going to symmetric difference and get a new basis. So sort of the schematic of things that can happen. We can start with I in S and not T. We are required to remove I. If we take J equals I, that's all we do. Or we can add J, or we can remove J. Similar if we start in I and T and not S, we're required to add T. Maybe that's all we do. Maybe we also remove some J, maybe we also add some J. So sort of like this middle thing, if we only let this middle thing happen, that's exactly matroids. But now we're letting other options into our lives. Just like matroids, we can talk about delta matroid polytopes. So this time, all of the edges of our convex hull are either in directions EI or plus or minus EI plus or minus EJ. So for example, if I take these subsets of 1, 2, 3, I end up with this polytope. And you can check that all of, right, so basically another way of saying this is we don't have any edges of length 3 or more, where by length I mean like 1 norm. And so here, there are no edges of length 3 or more. Like these are like EI plus EJ, EI minus EJ, yeah. But in particular, one thing to notice about this is that, right, so depending on which combinatorialist you locked in this hypothetical room, they might have, depending on how much they value this strong exchange property of matroids, it's possible that they came up with a definition like this, where we have to exchange the same things out of S and T, and both have to be bases. This does not satisfy that property. Right? If I take this vertex, and I want to exchange some things to get to new bases, here I want to take I equals J. And here I have to take I not equal to J. So in particular, there's like nothing I can exchange from both of these guys and end up with both being bases. So these delta matroids, they're a little weird, but they do have some relatively natural ways they come up. So for example, these come out of matchings on graphs. So I'm going to take my bases to be all sets of vertices where there is a perfect matching on the induced subgraph. Or equivalently, like you iterate over all matchings and you look at the vertices that are matched by each particular matching. So for example, if this is my graph, S is 2, 3, T is 1, 4. So the matching corresponding to S is just these two, matching corresponding to T. It's this one. I can just add 1 and 4 to S and then get the matching with both of those. And basically the exchange axiom comes from the fact that you can take like alternating paths in your matching. So if these are my two matchings and I want to add 7 to S, well, like the first thing I would want to do is just add 6, because that is what 7 is matched to. But then I can't do that because 6 is already in there. But then 6 is matched to 5, but 5 is already in T. And then 5 is matched to 4, but 4 is already in S. And eventually we get to 3, which is in S and not T. And so basically I can just take 3 out and then use the red matching instead of the blue matching on those remaining vertices. And so we get a matching that does that. So sort of like matroids, whenever you see delta matroids for the first time, they're like, look, graphs, they come from graphs. And then 2 seconds later, they're like, forget graphs, matrices are where it's at. So delta matroids also come from matrices. If I start with a symmetric or skew-symmetric matrix and just record which principal minors, so same set of rows and columns, have non-vanishing determinant, that will be a delta matroid. And we're going to call those representable. So the determinant of the empty minor, like by convention, is always 1. So in particular, the empty set will always be a basis of these. So, okay, calling something representable, like, yeah, this is a matrix, but also like representable for matroids means something very specific. So I feel like I should justify a little bit why we're allowed to call it that. And it turns out it's because it's essentially the same. So all matroids are delta matroids. You can see this because basically the exchanges we're allowed to do for matroids are a subset of the ones we're allowed to do for delta matroids. Or if you are like polytope fan, you can just say, oh, well, all of the allowable matroid edge directions are also allowable delta matroid directions. And it turns out that the notions of representability coincide. So a matroid is representable over K in the like Grassmannian sense, if and only if it's representable over K in this like symmetric matrix sense. And for example, this guy I showed you is a representable delta matroid. So if I take A to be this symmetric matrix that has zeros on the diagonal and ones everywhere else, can check that all of the minors are non-vanishing except for the 1-by-1 minors. And so I end up with this polytope. So in particular, like being representable doesn't mean we have like strong exchange or anything like that. So now, with that under our belt, I think we're ready to tackle valuated delta matroids. But first, are there questions on delta matroids? Okay. So when we defined valuated matroids, it was very nice. We had this like, already had this strong exchange condition, and then once you have a strong exchange condition, it's relatively easy to just turn that into an inequality, and then it turns out that that means it's like if and only if this minimum is attained twice, and it's also if and only if there's like a good subdivision. But I have already showed you that like delta matroids, strong exchange is too much to ask. So how are we going to define valuated delta matroids? So prior to this paper that I wrote, there was a previous paper by Felipe Rincon that talked about valuated even delta matroids. So before, remember, we were allowed to take I equals j, in which case we just removed one thing or just added one thing. Even delta matroids, basically it's the same axiom except we have to take j not equal to I. And some fun facts about even delta matroids. All bases are going to have the same parity. May or may not be obvious, but turns out to be true. And actually, this is an equivalent definition of even delta matroids. They're exactly the delta matroids where all bases have the same parity. They are also now the ones whose polytopes have edges and directions just EI plus or minus EJ. We can no longer have these EI edges because that would mean that the things on either end of that edge would have different parities. And perhaps least obvious of all, these now have the strong exchange property. So, I mean, this example I keep showing you of something that doesn't have strong exchange is obviously not even, because it has like both the empty set and 1, 2, 3. It turns out that like, not at all obvious, but even delta matroids do have this strong exchange property. And so one example of where even delta matroids might come from is if you're representable by a skew symmetric matrix, then all of your odd minors have to vanish. And so in particular, all of your bases will have even cardinality. So now that we have strong exchange, we get to define valuated even delta matroids by just, again, taking our strong exchange axiom and putting p's everywhere. So again, this ends up being equivalent to all edges being these like good delta matroid directions. It also has this nice local characterization. Right, so again, like if we take any two things that are like 4 apart, we know that the minimum can't be attained uniquely by those two things, because there has to be some exchange we can do. And so the minimum among, if we start with things that are 4 apart and we look at all possible exchanges we can do, the minimum has to be attained twice. And it turns out that like if we just check it on these like 4 cubes, that is enough. Sort of like for matroids, it was enough to check it on these octahedrons. Here it's enough to check it on these 4 hypercubes. And again, these, just like matroids, we talked about how they come from the Grassmannian, and then if we do the Grassmannian over a valued field, we get valuated matroids. Here, if we take our skew symmetric, right, because we want it to be even, matrix over your favorite valued fields, you end up with a valuated even delta matroid. So for example, if I take this skew symmetric matrix, right, so the empty set always has determinant 1, so that's valuation 0. You can check that these have determinant t squared, which will give us valuation 2, and that these two have have determinant 1, which is valuation 0, and then finally the whole thing has determinant t to the 4th. So in particular, right, we want to make sure that we don't have any length 4 edges, and how are we going to guarantee that? Well, any length 4 edge has to go between like s and s complement. And so as long as the minimum over s and s complement is attained twice, then like, right, if we're going to have an edge like that, then the minimum needs to be attained uniquely by that pair. And so here, the minimum is attained by both of these guys, and so we end up with like a square cutting through our hypercube. And in particular, that means we can't have any length 4 edges. Unfortunately, I can't draw in 4D, or I would have given you a nice picture of this. And then it turns out that for like small n, the size of our ground set, all of them are representable. For n at least 7, there are non-representable ones. For n equals 6, as far as I'm aware, that is still open. Basically, the way Rincon proves this for n at most 5 is there just aren't that many delta matroids on 5 elements. And in particular, it's few enough that GFAN is willing to finish the computation of what all of the possible valuated, or what all of the possible ones are, and like tell you what the possible valuated delta matroids on that support are. And then you can just sort of check that all of them are representable. So for n at least 7, there's basically you start having non-representable matroids, like the Fano-matroid. And then you can't represent them as delta matroids either. N equals 6, the computation is just too big for computers, or at least computers in 2010 to finish. Maybe now we can do it. Okay. But the eagle-eyed listener will notice that I just cheated, right? I was like, how could we possibly have valuated delta matroids? We don't have strong exchange. And then I was like, look at this nice case where we have strong exchange. So I still haven't actually resolved the problem. So now I will, though. Like, what if we don't have strong exchange? Well, for valuated matroids and for valuated even delta matroids, I did this thing where I was like, okay, here's the valuated strong exchange thing. And then I was like, and also this is equivalent to the subdivision having matroid polytopes or even delta matroid polytopes. And so what we're going to do is we're just going to turn that on its head. We're going to say definition is the subdivision is into delta matroid polytopes, and then see what we can say about it from that. So basically we have some function from the subsets of n to R union infinity, and I'm just going to ask that the induced regular subdivision is into delta matroid polytopes, or equivalently that all of the edges are EI or EI plus or minus EJ. And we're going to call this the delta Dressian, because matroids was the Dressian, so this should be the delta Dressian. So you can just put delta in front of it. So one thing we can say off the bat is that this will be a rational polyhedral fan in R to the 2 to the n. Why is that? Because it's a subfan of the secondary fan of the n cube. So the secondary fan, each cone tells you like different functions that give you the same regular subdivision. That's like the definition of the secondary fan. And then our delta Dressian is just defined to be certain good cones in this secondary fan, right? The ones that don't have edges of length 3 or more. So here's one function that is in the 3 delta Dressian. I'm going to take all of my even subsets at height 0 and all of my odd subsets at height 1. And I get this subdivision of the cube where I have like this orange simplex in the middle, and then sort of all the corners are their own simplices. So one thing to notice is like, okay, what do we have to worry about in the 3 delta Dressian? Well, I'm allowed to have any edges I want of length 1 and any edges I want of length 2. So really all I have to worry about are edges of length 3. And how can I get an edge of length 3? Well, it has to go between like S and S complement. And so in particular, any edge of length 3 is going to have to go through the exact middle of this cube. And since the exact middle of this cube lives inside this orange simplex, that means I can't have any edges going through it as long as I have this orange simplex. So this subdivision is a triangulation. So that tells us that we have a full dimensional cone in the 3 delta Dressian. Here's another element of the 3 delta Dressian. This time I have like 2 diagonals at height 0 and the 3rd diagonal at height 1. And so what I get is this orange square, or not square, orange rectangle going through the middle. And so again, I know that I don't have any length 3 edges because any length 3 edge has to go through this midpoint, and this midpoint is in the orange square. And so it turns out that like these are sort of the only 2 things that can happen. So I'm going to write down all of the things that might possibly contain this midpoint of the cube. And I'm going to basically say that we can't have the minimum among these heights attained uniquely by one of like SS complement. So either it has to be attained by 2 of the diagonals, or it has to be attained by 1 of the simplices. So there are sort of 2 flavors, right? Either it's attained uniquely by a simplex, or it's attained twice by 2 of the diagonals. So in particular, like this is a full dimensional cone in the secondary fan. This is codimension 1. It's a little weird, but it's fine. Okay, so now we've done the 3 delta Dressian. What happens if n is 4? So again, we can write down what it is. So, okay, I am now in the 4 cube, and I'm allowed any edges I want of length 1 or length 2. So I need to make sure I don't have any edges of length 3, and I need to make sure I don't have any edges of length 4. So this first thing says, right, if I have any length 3 edge, it has to live in a 3-dimensional face. And so by just making sure all of those are in the 3 delta Dressian, I know I don't have any edges of length 3. If I'm going to have an edge of length 4, right, so I'm going to look at all affinely independent sets that can, like, again, any edge of length 4 has to go through the exact midpoint of my cube. And so I'm going to look at all possible things that go through, that contain the exact midpoint of my cube. And I'm going to go to each one of them and I'm going to say, okay, if I were to give you this midpoint, what height would you put it at? And then we're going to have a nice little bidding war where each of them tells me what height it would put this point at. And then because we take the lower hull, like whichever one gives us the lowest bid wins. And in particular, so if we just don't want any edges of length 4, all we need is that it's not attained uniquely by like SS complement. But it turns out that like any of these guys are gonna have an edge of length 3 or 4. So in fact, so if it's attained uniquely by some other thing, then we're gonna violate this first condition. So the main reason why I want to write it that way is that like now we see that we can no longer be full dimensional. We have some minimum that has to be attained at least twice. And it turns out that you can just like write down a subdivision where this minimum is attained exactly twice and everything else is inequalities. So it's codimension exactly. Okay, so we've done 3, we've done 4. Perhaps we are bold and jump straight to n. Okay, so if I have a function on the n cube and I want to know that it doesn't have any edges of length 3 or 4 or 5 or n minus 1 or n, what do I need to do? Well, I need to make sure I don't have any length n edges. So I need this minimum over all things that contain 1/2 to the n, like the all 1/2 point to be attained twice. So in particular, I don't get any length n edges. And then I need to make sure that all of my restrictions to n minus 1 dimensional faces don't have any bad edges in them, which is just being in the delta Dressian of n minus 1. So we're done. Okay, we've completely characterized the n delta Dressian, except, okay, one thing that was perhaps conspicuously absent from the last slide is I did not actually write down any of these midpoint circuits for you. And the reason for that is because they are gross and not enlightening, and yeah. So like you can write them down. I think there are about 50 of them for n equals 4, but if you like mod out by enough symmetry, there's like kind of 3 different kinds. But still, like, okay. 50 is a number where I would be willing to write them down if I had to, but definitely don't want to. And that's for n equals 4, right? If we want to do this for like n equals 100, I don't even know how many midpoint circuits there are going to be. And like, not only do I have to like check the 100 midpoint circuits, but secretly inside this delta Dressian 99, I have to write down all the 99 midpoint circuits, and then all the 98 midpoint circuits. And I definitely don't want to do that. Again, these are things that you can compute. It's some sort of like linear programming exercise, but like, I would not recommend it for the sake of your sanity. So in other words, this is a characterization that does not spark joy. And so like for valuated matroids and valuated even delta matroids, there was this nice thing where like we didn't have to check everything, right? We could get away with just the octahedron or just the 4 hypercube. And it turns out here we can also get away with just the 4 hypercube. So if I have some function on the n hypercube, all I need to check is that if it's to R, so full support, then I just need to check the 4-dimensional faces. In general, if I want to let it not have full support, I am going to need to check that the support is a delta matroid, but beyond that, I just have to check the 4-dimensional face. So in other words, just like valuated matroids and even delta matroids, we again, like 50 is a number that like my computer would definitely be willing to check for me that the minimum is attained twice. And I do have to check that on all the faces, but still that's like much better than having to check the 100 midpoint circuits. Okay. So the last thing I want to talk about is how this ties in with this notion of representability that we've seen. So we saw before that like if I take a Grassmannian over a valued field, I get valuated matroids. If I take a skew symmetric matrix over a valued field, I get valuated even delta matroids. And so basically, spoiler alert, if I take a symmetric it's a wider class than that, some sort of matrix over a valued field, I'm going to get a valuated delta matroid, not necessarily even. So we're going to let K be any valued field we want, and we're going to say that it has an automorphic involution that preserves the valuation. So for example, I can take my complex Poisson series, the complex conjugation, sort of the way you would expect it to work. If you want to be a little bit of a troll, you can also use the trivial involution, which feels wrong on the complex numbers, but is allowed. It certainly preserves the valuation. If you want to suck up to your friendly neighborhood number theorist, you can do whatever this is on Q. It works, I promise. We'll see an example of it later. And then we're going to define Hermitian and skew Hermitian matrices to be basically what you would expect, but keeping in mind that our involution might not be, complex conjugation. So if A transpose equals A bar, it's Hermitian. A transpose equals negative A bar, skew Hermitian. So for example, over the complex Poisson series, if we take the trivial involution, this ends up being symmetric matrices, or skew symmetric matrices, or Hermitian matrices, or skew Hermitian matrices. Okay? And then theorem, if I start with something Hermitian or skew Hermitian, keeping in mind that this also includes symmetric and skew symmetric, over your favorite valued field, then this function taking determinants of principal minors will in fact be a valuated delta matroid. So in particular, if I take K to have the trivial involution and the trivial valuation, this tells us Boucher's result, right? That the non-vanishing principal minors give us a delta matroid. Because the trivial involution is just going to say we're going to remember what things are 0 and not 0. So for example, here's a perfectly good 3x3 Hermitian matrix over the complex Poisson series. And you can check that the valuations are 0 for the even-sized ones and 1 for the odd-sized ones. And so we get this triangulation again. Or if we take this to be our favorite, either Hermitian or skew Hermitian, doesn't matter, matrix, again over the complex Poisson series, now the valuations are 0 except for the 1x1 minors. The 1x1 minors are t, so those have valuation 1. You can check that all the rest have some constant term, so their valuation 0. And so in particular, we get this quote unquote bad, like no strong exchange delta matroid. So there are people out there, including some of the people who did a lot of the foundational work on delta matroids, who believe that valuated delta matroids should have strong exchange. Right? Somehow they take the matroid and the even delta matroid case where strong exchange exists and that's how you define it. And you can just sort of impose strong exchange, right? You can say, you can no longer impose that I is not equal to j, but still impose that strong exchange happens, and that's a perfectly valid definition, but somehow we've lost the connection to this representability in that case. And then again, if you want to impress your friendly neighborhood number theorist, take this two-adic evaluation. I claim that the empty minor always has determinant 1, valuation 0. The 1x1 minors here we can check determinant 1, valuation 0. I claim that the 2x2 minors have determinant negative 2, and the whole thing has determinant negative 8. Feel free to check my facts later, but this is what Wolfram alpha tells me, so it's probably right. And so right now we're taking the two-adic valuation. So negative 2 is 1 power of 2, so it's valuation 1. Negative 8 has 3 powers of 2, valuation 3, and we get this subdivision. So now all of the diagonals except for empty set 1, 2, 3 are all at height 1, and so we get this orange, not simplex, whatever shape that is in the middle, and then sort of these, here's the empty set, here's 1, 2, 3, are at higher heights. But in particular, the all 1/2 point is safely ensconced in this orange thing, so we don't get any length 3 edges. So reasonable question, when are valuated delta matroids representable? Turns out that on n equals 3, they're all representable, which is one reason, right? This strong exchange failure already starts at n equals 3, and so if they're all going to be representable by Hermitian matrices, then we should be allowed to not have strong exchange. In particular, they're represented by Hermitian matrices over the complex Poisson series. Already at n equals 4, though, we start having non-representable ones. And it's really just a dimension count. Right? We know that this space of the 4 delta Dressian is codimension 1, but the image of the principal minor map is codimension 2. So in particular, there have to be things in our codimension 1 thing that are not in our codimension 2 things. All right, so just to wrap up here, I went faster than I expected. Just some quick connections to other objects. So, okay, there's a secret second version, or I guess third version of Matroids that does show up in this talk, which is rank functions. And so, right, so the rank function, just you take a set and it tells you like what's the size of the largest independent set you can find in here. And it turns out that for any Matroid, this rank function gives you a valuated Matroid. It's some sort of submodularity thing guarantees that it has to give you the right edges. So here's the definition of the delta Matroid rank. It's a little bit weirder. We're going to maximize over all bases. So if it was just this like S intersect B, that would be more like the Matroid version, right? But one weird thing about delta Matroids is that I can take the bases of a delta Matroid and just like symmetric difference all of them by a fixed set, and that will give me another delta Matroid. And so somehow like I being in the set and I not being in the set is, I mean, if you do this to all of the bases, these are equivalent. And this, if you think about it in terms of polytopes, this is like some sort of symmetry of the hypercube. And so for delta Matroids in our rank function, we also want to count all of the things that are not in our set and not in a basis. And this makes it like invariant under this twisting action. And so it turns out, theorem, that if I take any delta Matroid and look at, I guess, negative rank to, since we're using the min convention, that will be a valuated delta Matroid. So here, these red dots are supposed to represent the bases of my delta Matroid. Unfortunately, because I can only draw in 3D, options are limited for how interesting this picture can be. And you can interpret this function as like, what is the distance to the closest basis, like along edges of the cube? So here, the things that are in our delta Matroid have rank -3. All of the things that are 1 away will have rank -2. And all the things that are 2 away will have rank -1. And then this is the subdivision that we get. And it turns out, basically, the polytope of our delta Matroid will always show up like as a cell in this subdivision. Okay, that's one connection. So basically, like, part of the point of this talk is like, this is the right definition for valuated delta Matroids. So in particular, if I take a valuated Matroid and just put those values on the hypercube and then like infinity everywhere else, that will give us a valuated delta Matroid in our definition because, again, all of the edges will be in the right directions. Also encompasses delta Matroids and in particular like representable delta Matroids, right? If I, again, trivial valuation lets me put any delta Matroid as a valuated delta Matroid, and if I start with something representable, I can, again, make it a representable valuated delta Matroid. It also sort of subsumes Rincon's work. And the even case, this is like a recurring thing in delta Matroids. The even case is always way nicer than the general case. And so there's a lot of things that Rincon can do that like we can't necessarily do. But in particular, if I start with a valuated delta Matroid and impose that it has like constant parity on its support, then it's like if it satisfies our definition, if and only if it satisfies Rincon's. And we also, again, get this like finite characterization where we only have to check the 4-dimensional faces, just like he does. And the last thing, which is something I did not touch on in the rest of the talk, but sort of this like Hermitian, skew Hermitian, symmetric, skew symmetric thing is like secretly saying something about the Plücker vectors of isotropic linear spaces. And so we show in almost all cases that these Plücker vectors will give us valuated delta matroids in our sense. And when I say almost all, there's like a weird thing that happens sometimes in characteristic 2 that we have not been able to resolve yet. But thank you very much for your attention.
Thank you. If there's any questions, please wait for the mic.
You mentioned there were some things that happened for even delta matroids that you haven't been able to generalize. Could you say a bit more about that?
I think it's more just like, well, for one thing, like even delta matroids generalize to like M-convex functions on jump systems. And we don't know what the generalization of this to jump systems would be, for example.
Perhaps on a similar line, matroids have like a nice duality theory. When you keep going, like, you know, you kept adding adjectives there to evaluated delta matroid or to evaluated matroid and delta matroid and then both. Do you still have, like, do you have duality all the way? Do you lose it somewhere? Like, do you have like a dual notion, like the dual evaluated delta matroid or the dual delta matroid?
I mean, I guess if we were to directly take dual to dual, right, that would just be taking complements of bases. And so that's just twisting by the ground set, right? Symmetric difference every basis by the ground set. And you get, I guess, the quote-unquote dual delta matroid. And so it would just be like, so that should still give us a valuated delta matroid because it's just like inverting the cube.
Okay. Thank you.
Yeah.
Other questions? All right, so before we thank Tracy, in case there is any momentum to go to the grad house, Tracy doesn't know where it is. So if anyone wants to sort of spearhead that charge, please make sure you bring her along. And with that, let's thank her.